we'll do review and whatever problems you want for the last part. Here's what we're looking at in vector functions. It's a pretty easy section. I just want to make sure I completed it all. We said last time that we're going to focus the lines. The one thing that is important to know. We've already done these really. If we have a line through a point, x0, y0, z0 with direction vector ABC. We can write immediately that x of t, y of t, z of t before was x0, y0, z0, the vector to the position, plus t times the direction vector, right? And the picture was this. You take a vector r0, you call this r0. To any point in the line whatsoever. Then you take the direction vector v, you take this vector plus any multiple of this, you can get anything you want, right? Take t times v and take it out here, and just put end to end. This one plus t times this one. This is that point to equal y. So it's not very important in the line is t scales needle. T really is longer or negative. Sweeps out the line. That's what we said before. Now we'll just call this result when we take r0 plus t times v, a vector value function. Because you're putting in another t and getting out a vector. If you multiply this out and group it, this just becomes x0 plus at, y0 plus bt, z0 plus ct is the vector value function that will sweep you along the line. You don't have to use an isolator set up like that. You sweep out the lines in other ways, but this is the way I'm going to do it because it's easiest. And then whenever you recognize a vector value function equals a number plus a number times t, number plus a number times t, number plus a number times t, you recognize it's sweeping out a line because it can be put back into this form. Last one kind of problem. Here's an example. We're going to want to find a vector value function r of t that t evolves out and sweeps along this line in its terminal point, sweeps out the line. That's the idea. R of t is a vector value function whose initial point is at the origin. Its terminal point moves along whatever term it is in line in this case, and sweeps out the point. Suppose I want to find a vector value function for the line through 1 minus 1, 1, and 2, 4, 3. All right. Wonder what the vector value function is that sweeps out the line through 2 points. Well, it's pretty easy, right? I just have to find a direction vector by subtracting these two is a good way. I subtract 4, it's 2 minus 1 is 1. Well, let's do it. 4 minus a minus 1. And 3 minus 1. Gives me the direction 1, 5, 2, right? So there's a vector along the direction of the line from point 1 to point 2. So R of t, I'm taking either one of these 2 points. Let's take the easy one. It's the vector to this point, so I'll put angle brackets that sort of round. Round refers to the point, and angle refers to the vector from the origin to the point. So this is 1 minus 1, 1 plus t times the direction vector 1, 5, 2. If I left enough room here. Gives me, let's say, 1 plus t minus 1 plus 5t, 1 plus 2t. Here's a vector valued function, because you put in t, you get out a vector. Right? Here I get 1 minus 1, 1, the original point. If I put in t equals 1, I get 2, 4, 3, the other point. And if I put in any other number, I stick out points along the line that contains those 2 points. Here's a vector valued function. Okay? But it's varied between plus and minus infinity, so you got the line. Any questions on that one? And T, sweep out a line. Another one is circles. So we said circles are real important too and real common in parametric curves. And that came out of their parametric form comes out of the unit circle. Remember we said last time, just to remind you, the circle, I did the lines in 3-space by the way, because in 2-space they're easy. You can use your old algebra stuff, like y equals x plus b. All this work that we do for lines here works, but it's not easier. And the plane, we usually use slope intercept or 2.5 or something like that. But in 3 dimensions and higher, we use vector parametrics like this is here. Circles, although the plane here comes out of trigonometry, right? In trigonometry, we said, I hope I'm not repeating too much, but if you have an angle t, then the coordinates on the unit circle, radius 1, where that ray at angle t in center position intersects, is cosine t sine t. That's the way you define sine cosine. It extends the natural dimension of the triangle, the word for any angle. Now, if you keep extending this out to some sort of radius r, then it's exactly r times as far out, and so now it has coordinates r cosine t, r sine t, and then furthermore, if you translate this over, so it's not centered at the origin, like if you put it over here, you just have to add the new coordinates here, x or y are at every spot. And now, the vector will point in a circle like this. In this case, we want you to have the vector here plus the vector here. I translate this one over. And so you have the vector r0 to this point plus this one. You get this. R0 in the translation plus r cosine t sine t gives you an equation for the circle. So for example, let's say find a vector valued function for the circle at the point minus 1, 2 of radius 4. I just put, oh, r of t must be the translation, minus 1, 2, that vector moves the r cosine t, r sine t circle, and I just have to add the circle to that, r, which is 4 cosine t, r sine t. There's a vector valued function for a circle. Radius 4 and minus 1, 2. And what happens is you're taking this vector to go to the point and then adding to it that vector that rotates around the circle. Switch it up. You can combine these together and then you get minus 1 plus 4 cosine t, 2 plus 4 sine t. And t only has to run from 0 to 2 pi to sweep out the circle, so usually we do that. Otherwise, you run it over and over again. There's an example of a circle. So you say, fine. Now the circle parallel, two lines like that mean parallel, to the YZ plane that go through the point 1, 4, 7, and let the circle have radius 2. How can I find that one? Now I'm going to do it in free space. Why is he flying? That means it's x equals constant, right? Well, it contains this point. It must have the. It must be the plane x equals 1. All right. That's the plane that's parallel to the line that contains 147. That tells me I can write RFT like this. RFT has constant x coordinate 1. But now I need to arrange two circles centered at 4, 7. I'll do the same thing I did here. Right, x. This is essentially x0 plus r cosine t, y0 plus r sine t. And this one, now I want to do it in the yz plane, so let's call it y0 plus r cosine t, z0 plus r sine t. I know it's going to look at that form because it's a circle. Now I just need to figure out y0 and r. Well, I have the radius is 2, and I have that it goes shouldn't say through, and they should have said at before wording it. It's supposed to be the circle centered at this point. All right. So this is the set. This is x, y0 and z0 is 4 and 7, and I'll just call this 1, 4 plus 2 cosine t, 7 plus 2 sine t. So this vector at the origin sweeps out the circle in 3 dimensions within the plane. But the object is to be able to see this stuff when you see r cosine and r sine. Imagine it's sweeping out a circle somewhere along the way. It all look okay? Then they gave me some trickier problems, visualization and so forth. How about this one? So be a little more exotic then. Parameterize. In other words, write the vector parametric form. The intersection of these two things, x squared plus y squared equals z squared, with 6y equals z squared. I think it's kind of nice to visualize it so the instructions don't say you have to. What does this one look like? This is for the test, actually, this part. Z squared equals x squared over a squared plus y squared over b squared is an elliptic cone. And if a equals b, it's actually a circular cone. So this is like an hourglass. So z is the one that's on the side by itself. It's an hourglass like this around the z-axis. So there's the elliptic cone. Circular cone. Now what's this one? 6y equals z squared. Yeah, the YZ plane. There's a variable X thing that cylinder, right? You extrude it the other direction and X the counter current is not restricted. So you draw the parabola y 6y equals z squared in the YZ plane, which is the easiest plane of the board here. It's y equals 1/6 z squared, and it looks like this. Well, that's not good. And then let x be arbitrary and slide in like this at the top. The same parabola cross section. Now that has an intersection. That means the cross intersects the cone. What does that intersection look like? How do I parameterize it? Well, it's something exotic like that. This is just showing you can parameterize curves of intersections. Here's what you can do on this one here that has only two variables. Let t be one of these things. Probably easiest to let z equal t. Otherwise, if I let y equal t, then z comes out to be a square root, which is messier. So I'm going to let z equals t. And then I notice that y is 1/6 t squared. Since this only has two variables in it. Now I can plug both those into x, right? So I'll plug that into here and get x squared plus y squared is 1/6 t squared is squared, right? It's y squared equals z squared is t squared. So evidently, solving this for x, I've got x equals plus or minus the square root of t squared minus 1/6 squared. T to the square root of the square is t to the fourth. Well, I wind up with a little algebra from this step, solving that for x. I think in the one side, I think it's positive. So suppose x is non-negative, at least. Then we can use the plus sign. All right, so one last one. I'm think about what I was going to do today. And a lot of these are going to have you sketch it based on eliminating a parameter, right? Sometimes it's nice to get that parameter because we're going to be able to do calculus with it. If you can write the circle as a function of a parameter, and you find the tangent to the circle, and it tell you the parameter instead of having to find all two or three variables along the edge. But sometimes it's nice for sketching purposes to be able to go back the other way. So we'll say, suppose r of t is sine t, cosine t, 8 sine t, plus 6 cosine t. And I said, project this onto the xy plane and write its equation. Oh, I'm sorry, it's XZ plane. So the idea, whatever this curve looks like, and this isn't what it looks like. Suppose it looked like this, like a helix or something, around and around. What's its projection in the XZ plane? It's like you have a light shining here from infinity, and all these things project parallel, and maybe in the XZ plane, over here, here's X and here's Z, it shines into a circle. So it looks like you're going around and around in a circle in a projection. That's the idea. And the way you do that is you just drop out the y coordinate. So the projection, you just forget the y coordinates. You have x equals sine t, and z, I miswrote this, it's 6 cosine 2t. Got a right meter. Z equals 8 sine t plus 6 cosine t, 2t. Well, the object is just to eliminate the parameter one way or another. So I could do something like this. I could substitute this one in here and get rid of that sine t, but what do I do with the rest? I just have to find, in this case, a trig identity works well. So I'll rewrite z is equal to 8 sine t plus 6. I'll write cosine 2t as 1 minus sine squared t. I'm sorry, 1 minus, it's cosine squared. I'll write this one first. T minus sine squared t. Using a trig identity that cosine 2t is 1 minus cosine squared minus sine squared. And now you remember cosine squared is also 1 minus sine squared. So this is 8 sine t plus 6. 1 minus sine squared. Minus sine squared again is 1 minus 2 sine squared. I can do that in one fell swoop. Which may remind you, oh yeah, there's that other identity for cosine double angle is 1 minus 2 sine squared t. That comes from doing these two steps. Now I've got it because now this is 8x plus 6 minus 12 x squared, right? Sine squared is x squared. And you recognize finally minus 12x squared plus 8x plus 6. Oh, it's a parabola. I can sketch that, right? Ax squared plus bx plus c. You can complete the square, find the vertex, all that stuff. But there's the equation. Is that z equals this function, this parabola. This is how this one projects. This one doesn't project a circle like this. This projects whatever it moves like out of here, we're not sure. But over here, projection is to a parabola. And finally, I want to mention it's not in a section yet, but it's coming up soon. A lot of these use trig functions to get rid of the parameter. For instance, if I put this one, I said, what is the equation of the plane r of t equals 2 sine t 4 cosine t. Looks kind of like a circle, right? Except what's not good, or what's not a circle. This one has a 2 and this one has a 4, right? No longer is it r sine t, r cosine t, r sine t. It's something different. And if you think about it this way, you want to know what that is, you can eliminate the parameter using a trig identity. This is x is 2 sine t. This is y, right? X is a function of t, y is a function of t. Is 4 cosine t. If I took x squared over 2 squared plus y squared over 4 squared, what would I get? Now I'm getting the lift here. I'm jumping ahead of my final answer here. X squared over 2, x over 2 quantity squared is sine squared, right? Let's set this up so this is sine squared. Y squared over 4 squared is evidently cosine squared. And sine squared plus cosine squared is 1 by the Pythagorean identity. So we observe that all these points lie on the ellipse. X squared over a squared plus y squared over 2 squared equals 1. We just fix this quite easily in the plane. This is the ellipse that semi-axis joined to. And as t goes around, t is no longer the whole angle like it was for the circle, except for one of the axes it happens to be. But it still sweeps out the ellipse as you go into the coordinates. That's how you can eliminate the parameter using trig identity. One last one. If I put r of t equals, let's say, secant t, tangent t, what does that sweep out, do you think? This time you remember trig identity that says tangent squared plus 1 equals secant squared. Remember that? That's another Pythagorean identity. You get that from dividing sine squared plus cosine squared equals 1 by cosine squared. And you get this if I writing that one by cosine squared. That's sine squared over cosine squared is this one. Cosine squared over cosine squared is this one. 1 over cosine squared is that one. That means you can do a trick with this. If this is x of t and this is y of t. If you let's say y squared minus x squared, you get tangent squared. How much is x? Doesn't matter. X squared minus y squared. That's easier. X squared minus y squared, you get secant squared minus tangent squared. Right from the parametric curve. But secant squared minus tangent squared is evidently equal to 1 from this equation, right? You subtract tangent squared. Y equals secant squared minus tangent squared. So you can use this other Pythagorean identity to show that actually this parameter right is a hyperbola, right? X squared over 1 squared minus y squared over y squared equals 1. It's a hyperbola opening in the x direction with a equals b equals 1. Well, finish with that one. Those things on the parametric curve. That was something I've actually done this semester. I should go to one after. Now that in mind, we talked a little bit about the test at the beginning. Here, particularly, also we'll look at also the reducing homework. We'll do them all, right? If you haven't got them, download them from Canvas. They're under Files. So we go to the Files uh, label on the side there. How about this? Find the vertices, foci, and center of the ellipse x minus 1 over 4 squared plus y over 9 squared equals 1. How do I do that? This is just the standard equation for the ellipse shifted with x replaced this is a center. If I didn't have this minus 1 here, it would be at 0, 0, right? But if I replace x by x minus x 0 and y by y minus y 0, then it's just at x 0, y 0. So the center here is whatever is subtracted is 1, 0, right? That's the center. And then from that point, you can think of making a substitution. X bar equals x minus 1, y bar equals y minus 0. And say this is x bar and y bar. At the origin of x bar and y bar, I now have a equals 4, b equals 9. Once I have a and b, I can find the focal distance, right? Because a squared equals b squared plus c squared. Wait a minute. I got this backwards. A is 9 and b is 4. Since the a is always has to be the larger number for the ellipse, not so for the hyperbola, but for the ellipse. A is 9, b is 4. A squared equals b squared plus c squared tells me that 9 squared equals 4 squared plus something squared, right? Evidently, 81 minus 16, 65, right? So C is square root of 65. Is the focal length. Because A is under Y, the vertices are vertical from the center. A, the bigger number, is under Y. So the foci are going to be at the center, 1, 0, plus or minus 65 in the Y direction. They're going to be at 1 square root 65 and 1 minus square root 65. I like to visualize this stuff. I think it really helps. Center's right here at 1, 0. And the vertices have to go up and down with the bigger numbers every Y there. And square root 65 will be the 8, so it's up there somewhere. Both sides, sorry about that. So they're up here down here. At 1 root 65, 1 minus square root 65. You can sketch this because it has A equals 9, that's the sum of major axis, it goes to 2, and then 2 equals 4, it goes on 4. 1, 2, 3, 4 goes to minus 3 here, except the center's going to be, you know, 1, 2, 3, 4, 5. And so it goes something like this. There's the ellipse, there's the foci. It'll go off. Now the vertices are at the ends of the axis. You got here, here, and here, and here. You're going to start to look at it and see more than you do the arithmetic. You got to 4 minutes, you get to minus 3. So the vertices, I got minus 3 throughout. I'm moving 4 minutes left. Plus 5 throughout, I'm moving 4 minutes right. 1, 9, I'm moving 9 minutes out. We got a minus 9. Oh, no. Yeah. 1, 9. The last one here. Right? And cylindrical coordinates. So they have 4x squared plus 4y squared minus z squared equals 1. What's the easiest way to do that? Well, you can bring in equations, you may want to use either set of conversions. You can put in x equals r cosine theta, y equals r sine theta, and z equals z, and it would work. What's even easier? Well, notice this is just 4 times x squared plus y squared. Z equals z just translates directly, right? In cylindrical coordinates. But x squared plus y squared is r squared, so it's 4r squared minus z squared equals 1. They're in one fell swoop because r is root x squared plus y squared. This must be r squared. If you use those transformation equations for r and it's faster. So use whichever equations make it faster. If I put x equals r cosine theta and y equals r sine theta, that won't work. I just have to use trig identity to reduce it afterwards. Here's what you can make it for yourself if you take it into classes. Stretchy string and a couple peanut butter candlers. If you twist it, what's that? Put it over here. Oops. Mess it up. Yeah, it's a hyperboloid of one sheet. You can put this in here. I put this in my car and smashed it one day. It used to work perfect. So for the people online, you can twist this thing and make a hyperboloid of one sheet. It's called a lineal surface because you can make it out of lines, and this little thing proofs it without words even, right? You can see the strings are still lines, and they make up the yeah, it's the hyperboloid of one sheet. Its standard equation is x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. It looks just like the ellipsoid with one minus. And then it looks just like that figure you just saw. It opens in this form with z being negative. It opens about the axis like that. And this cross section here in the z equals 0 plane has semi-axes A and B. That helps you to sketch it right at the waistline there, the smallest one. If you put z equals 0, you get the the trace, we call it. That's this ellipse in the xy plane. Hyperboloid of two sheets. Too many equipment failures. Has two minuses. Right, so you start with the ellipsoid with no minuses. The hyperboloid of one sheet has one minus. The hyperboloid of two sheets has two minuses. Usually we put them on the x and y though. We put minus x squared over y over a squared minus y squared over b squared plus z squared over c squared equals 1. This always looks better when you see it the second time. This one also opens up and down if you put the minuses this time on x and y. But again, it's two minuses make a hyperbola of two sheets. One minus make a hyperbola of one sheet.
Doesn't matter where the minus is.
Yeah, if the minuses are on these two terms and the y is positive, it opens about the y-axis. So if you put the z term as the positive one, it opens up and down like this. And you try and figure out, well, let's see, if x and y are 0, then I just have z squared over c squared equals 1. So this must be 0, 0, c, and this must be 0, 0 minus c. And then you can do cross sections, right, of this thing if you take z a little bigger. So but this one looks in two pieces, so it's hyperbola of two sheets. You have ellipses in parallel to the xy plane in both cases, but here the hyperbolas go up like this, and this is also a hyperbola here and here. And this one, the hyperbolas look like that, and also in here like that. Well, I think we're out of time, I guess. Feel free to contact me if you want to set up some office